Well, the discovery of electrons led to more questions. And this is typical in science. You're investigating something, you figure something out, and that's not the end of it. That just opens more questions. It's endless, which is pretty awesome if you like solving problems. There's just an endless series of problems to be solved and figured out. So if there's negative particles in an atom, and they knew that atoms themselves were not charged, there must be something positive in there to balance that negative charge. And then how do those positive and negative charges fit together in an atom? What's going on inside the atom? Well, Thomson, the cathode ray guy, came up with this, what's called the plum pudding model. Have any of you ever had plum pudding? It just sounds weird, doesn't it? It's a British dessert, okay? So the closest thing we have to that in America would be like a blueberry muffin. So there's blueberries kind of randomly distributed through the muffin, okay? So we'll call it the blueberry muffin model. And his idea was that the atom has electrons, the negatively charged electrons. Those are like the blueberries in the muffin. They're just kind of randomly distributed. And then most of the atom is this sphere of positive charge. That's the muffin part. Okay? You have to start somewhere with models and theories, right? So this was his theory. And of course, you got to test it. Around this time, radioactivity was discovered. Radioactivity, which will be studied in Chapter 19 if you continue into Chem 1B. Radioactivity is the emission of small energetic particles from the core of certain unstable nuclei. This was discovered at the end of the 19th century. And this discovery allowed scientists to probe the structure of the atom. There are three, well, we know there's more now, but at the time there were three known types of radiation: alpha particles, beta particles, and gamma rays. The one that we're interested in here are the alpha particles. Alpha particles have positive charge on them, and they are the most massive of the radioactive particles. So, Rutherford. Rutherford was a student of Thomson's, and he set out to do some experiments to validate Thomson's plum pudding or blueberry muffin model of the atom. So what he did is he took positively charged alpha particles and directed a beam of these at a very thin gold foil. And the plum pudding model predicted that these massive particles moving at high speed would just go straight through the atom. Think about tiny particles going very fast, shooting at a muffin, right? They're just going to go straight through. This is what he expected to happen. So this is an illustration of the setup. Here we have a source of these alpha particles, very thin gold foil, shooting the alpha particles at it, and then this thing along the side is a detector, so that when these alpha particles come through, they make a little tiny dot of light so that you can see where they hit. And what they found is that, yeah, most of the particles came through. Some of them were deflected significantly. These guys, they deflected a little bit. Maybe they grazed a blueberry, right? But mostly they went straight through. Some of them were deflected significantly, but what was very surprising is some of them bounced back. They were deflected through very large angles. These results were unexpected. Approximately 1 in 20,000 of these particles bounced back. And Ernest Rutherford said this was about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you. 15-inch cannonball fired at a piece of tissue paper. That's just going to blow right through the tissue paper, right? You would be shocked if it bounced off tissue paper and hit you in the face. This was how surprising these results were. So obviously, something's wrong with the model. The experiment tells us this model cannot be correct. So what do? You you come up with a new model to explain the new results. And that's what he did. So this was his plum pudding model, the predicted result going straight through. Based on the results of this experiment, he came up with a nuclear model. He concluded that matter cannot be as uniform as it appears. It must have large regions of empty space and small regions of very dense matter. So he proposed that there is a nucleus. So this fuzzy yellow here is the atom. There's a nucleus in here, very small, very dense. And his theory was that when these alpha particles hit the nucleus, because it is so dense, it's like an immovable object, they just bounce off. Like someone running into a brick wall. It's immovable, you're just going to bounce off. And this nucleus is composed of protons and neutrons, and we'll get to those in a minute. Any questions? So, the nuclear theory of the atom. Most of the atom's mass and all of its positive charge are contained in a small core called a nucleus. Most of the volume of the atom is empty space, and in that empty space we have tiny negatively charged electrons that are dispersed. This says nothing about what those electrons are doing, they're just out there somewhere. There are as many negatively charged electrons outside the nucleus as there are positively charged particles inside the nucleus, so that the atom is electrically neutral. We now call these protons. So this model was highly successful in that it explained observations. It explained why some of those particles bounce back and yet most of them go through. It explained everything that they knew to date. But it was still not quite complete. One of the problems was a hydrogen atom has 1 proton, a helium atom has 2 protons. And atomic theory says that these protons, that's where the mass is in the nucleus. And based on the knowledge of these number of protons, you would expect that helium would weigh twice as much as hydrogen. But it actually weighs 4 times as much. So, not complete. So, later work, still by Rutherford and another of his students, James Chadwick, demonstrated that the previously unaccounted for mass was due to neutrons, that there was another particle inside the atom that also had mass. So neutrons. Neutrons have no electrical charge. They're neutral. Isn't that nice? Neutrons are neutral. No charge. Neutrons have a mass that's very similar to the mass of a proton. And so this explains the mass difference between hydrogen and helium. So hydrogen has 1 proton, it has no neutrons. So it has 1 massive particle. Helium is 4 times as massive. It has 2 protons and 2 neutrons. It has 4 massive particles. 4 massive particles should weigh 4 times as much as 1 massive particle, right? So this explains that difference in mass. This does not contradict Rutherford's atomic model, but it just adds to it. So the nucleus is extremely dense. It's actually really hard to get your mind around how dense the nucleus is. But it has over 99.9% of the mass of the atom, and yet it occupies very little space. So your book talks about how atoms are like clouds. So we think of a cloud. A cloud has little tiny droplets of water in it, right? Those little tiny droplets have negligible mass. They themselves do not take up much space, and yet they occupy a great volume, right? So electrons are like water droplets in a cloud. Their mass is so small that it just really doesn't even matter. But they're dispersed over a large volume. So clouds and atoms are mostly empty space. The nucleus, if you had a group of nuclei the size of a period, yeah, go ahead and shut those doors if the next class is coming in. If you had nuclei crowded together the size of a period on a printed page, it would weigh millions of pounds. A period weighing millions of pounds. It is so incredibly dense. So if atoms are mostly empty space, why does matter seem solid? I mean, you can hit your fist on the bench top here. That seems pretty hard, doesn't it? You bang your head on that, it's going to hurt. Well, matter appears solid because the variation between the dense nucleus and the non-dense electron cloud, the variation is on a size too small for our eyes to see. So what does that mean? Well, let's think about, imagine for a minute, scaffolding, right? Like they put on the outside of buildings when they're building it up. And it's very open, right? You've got these posts and boards and stuff, but it's very open. It's mostly empty space. Imagine scaffolding the size of a football field and 100 stories tall, right? That's massive scaffolding. Mostly empty space. If you flew over that in an airplane, though, and looked down at it, it would appear solid because you are so far away from it that you can't really see the difference between the boards and the posts and the empty space in between. So we look at this, and hopefully we get a picture, an idea of how looking at this from a great distance, it looks solid even though it's mostly empty space. And when we look at matter, we can't see the variations because the variations occur on such a small distance, on such a small scale. And yet matter is mostly empty space. If we had this ginormous scaffolding and that represented an atom, the nucleus would be the size of a pea in the center of it. So we've got almost all the mass in the size of a pea, and the rest of that volume, scaffolding the size of a football field, 100 stories tall, is a few electrons with negligible mass. So mostly empty space. Any questions? That should make your brain hurt a little bit. What? That's crazy. Yeah, it's really, really crazy.